Thanks for the introduction. I'm Bede, and I'll be discussing PeakForce Tapping with ScanAsyst, a mode that has been available for some time on the Dimension icon, but has only been recently released for the Dimension Edge. The Dimension Edge is a high-performance AFM that is based on the Dimension icon head, but is available at a lower cost than the Dimension icon, making it an extremely good value. In fact, I would call it the best valued closed-loop Dimension AFM. Closed-loop accuracy and noise levels are comparable to open-loop AFMs. Noise and drift performance is competitive with small sample AFMs. However, it has a modular design for excellent price-performance ratio. The Dimension Edge has solutions for all applications on any sample. Its open stage design allows easy access to sample for custom experiments as well as large samples. Dimension Edge offers the full suite of Bruker AFM modes, and custom measurements are possible with its built-in access to signal routing. The Dimension Edge is a high-performance system for any user. Stage and high-resolution optics provide fast sample navigation and automation. The workflow is designed for ease of use and high productivity. And now ScanAsyst auto-optimization allows even infrequent users to obtain expert results. How does ScanAsyst work? Before we dig into that, let's take a minute and discuss the operation of atomic force microscopy in general. On the left here we have a diagram showing a typical AFM with a sample and a tip, which is very sharp and can localize the interaction between the tip and the sample. There's a scanner which allows the sample to be moved relative to the tip in both X, Y, and Z. There's a controller which implements a feedback which keeps some signal constant, like the deflection of the cantilever. This would be contact mode. Basically it's moving Z, the Z piezo, in order to keep that deflection constant. The sharp probes in close proximity to the surface used in AFM allow many phenomena to be localized at the nanoscale, and this allows mapping of sample topography and properties. For example, atoms and molecules can be visualized. This is at length scales far below the diffraction limit of light. Physical interaction between the tip and sample enables direct nanomechanical 3D metrology. So, for example, you can, if you move the Z piezo back and forth or up and down, you can and measure the deflection of the cantilever simultaneously. You can make what is called the force curve, and basically initially you're not touching the surface, so there's no deflection of the cantilever. When you come near the surface, attractive forces causes it to the tip to jump into contact, and then the tip stays on the surface while approaching until it reaches the peak force, and then retracts, and at some point the tip breaks free of the surface at the pull-off point, and then it goes back to undeflected. Analyzing these curves can allow you to get information about the mechanical properties and adhesion of the samples. Additionally, if you attach an electrical connection to the tip and sample, you can get electrical information such as work function, conductance, capacitance, and dopant mapping of your sample. Now, contact mode has one weakness, and that is that there are lateral forces on the tip which can cause tip wear and sample damage. So in the early 90s, we developed tapping mode AFM to preserve the tip and sample. In tapping mode, the cantilever is oscillated near its resonant frequency by a oscillation down here at the base of the cantilever. So the cantilever is vibrating, and the tip is approaching the sample and then moving away from the sample at roughly the resonant frequency over a wide range. So when the tip approaches a sample, it experiences an attractive force and is pulled toward the sample, and then basically it jumps into contact with the surface, and then the repulsive, like Coulomb interaction dominates the response of the tip. The tip is then retracted, and this is all happening at the resonant frequency of the cantilever. The contact time is very small, so around tenths of a microsecond or less, so there's no time for lateral forces to build up. It was also quickly discovered when we started doing this mode that the phase of the tapping response contains some information about the material properties of the sample. Tapping mode phase imaging, while experiencing these interactions, does not actually measure this force curve, however, or the direct forces between the tip and sample, for that matter. The AFM tip oscillates back and forth on this curve over a wide range, far from the sample. This is typical amplitudes are tens of nanometers to around 100 nanometers. The AFM tip oscillates back and forth on this curve, interacting with the sample, but forces are convoluted with the transfer function of the cantilever, filtering out frequencies away from the resonance and reporting only an average response of many interactions through the lock-in amplifier. While this is in no way detrimental to basic imaging, it restricts the information beyond sample topography that can be gained and unambiguously assigned to a certain sample property. This is unlike the previously shown force curve, during which one has direct control and is able to extract useful sample information. In PeakForce Tapping, by contrast, we have direct force control, and we are modulating the tip position here with the sinusoidal motion. This gives us the greatest possible ramp rates without exciting piezo resonances, and we do that. But we do this at well below the resonance of the cantilever. So this sub-resonance modulation of the tip avoids the filtering effect of the cantilever transfer function. So we can actually see the entire curve. Here it's plotted as a function of time. We have the deflection of the approach and then the retract along time that occurs during a 500 microsecond time at 2 kilohertz while we're moving our Z modulation at 2 kilohertz. In the right curve, we have actual data here where we've set the system to feed back at a very small interaction force. So you can see real data here as plotted as a function of time, and this is a sub-nanonewton interaction force. The feedback benefits from prior curves and does not disrupt the sinusoidal piezo motion by attempting to reverse the ramp direction during the partway through the ramp, which that in combination with the other features of the mode provides lower force during imaging, higher resolution, and new information about how to what the sample properties are. And then finally, this makes it possible to make it easier to use also. The whole curve is available for analysis since it is not filtered by the cantilever transfer function. With some minimal processing, the deflection data in the previous slide can be converted to a force curve, as we see here on the right. basically during the approach we have no force, and then it comes into contact, and then it's on the surface, and then retracting it comes back down, and we have the adhesion point, and then it breaks free of the surface, and we're back to zero force. So the adhesion image is coming from basically measuring all of the, for each of the interactions, measuring the value of deflection at this point. And we can make a map of that. As you see here on the left, you can see that in this polymer composite, this component here with the circle, inside the circle, has a significantly lower adhesion than that of the matrix of this polymer composite. PeakForce Tapping is the technology that we've been talking about behind these new modes. So as we scan across the sample, we're controlling the force at the peak of that force curve, the peak interaction force between the probe and the sample. And we can control this peak value to less than 100 piconewtons. This is often lower than tapping mode on the same samples. The peak force of each of these curves is monitored, and then that's used as a feedback signal. If you combine that functionality, PeakForce tapping functionality, and you automate the setting of the set point and the gain of the system, we call that ScanAsyst. That's the fully automated, optimized mode based on PeakForce tapping that we're offering with the Edge. So if we're working with very small peak forces, we should expect that the tip should be preserved over a long period of time, and we should be able to obtain high-resolution images over many frames. So for an example, we image this polysilicon sample, which is usually very, it's rough and it's difficult on the tip. However, the automatic image optimization is resulting in very consistent results and without wear, and there's no adjusting parameters, so you get to those results faster even if you're a beginner. The direct force control allows the system to protect the tip and the sample from damage, and there's no tuning of the cantilever resonance or anything like that, making it easier to get started. But let's take a look at the images. So here's image number 1. After 10 images, really it's indistinguishable that there's been any change. And then even after 20 images, we still have pretty much no change, and we're still getting beautiful images. So that's a result directly of that PeakForce tapping feedback. Now, another thing we did to make the system easier to use is we organize the workflow within the user interface. So basically, along the top of the toolbar in the user interface, you'll see that you have step 1, 2, 3, and that's engage. So basically, if I click on step 1 here, a selection dialog here pops up, and I can choose my PeakForce tapping mode, or I can choose other modes if I'm going to do a different type of experiment. And then I just hit load experiment, and then I'm ready to hit engage, and it'll start scanning, and I get my PeakForce tapping can automatically set up my parameters for me if I'd like. As I mentioned, the ScanAsyst automatically can set my parameters, and it does it constantly during imaging. However, advanced users can switch to manual and obtain full control of things like the PeakForce amplitude and the PeakForce frequency. so that you can do experiments with varying force or varying amplitude or frequency to see if there are any differences for your sample. So looking at a polymer brush, these are PBA polymer brushes, which are these polymer chains that have a backbone, and then there are short brushes coming off the backbone, and the chain is tethered at one end to a surface. And these are used. These have been an interesting but challenging sample for SPM, and even since the 90s. Basically, it's often used in industry as because it's got the capability to regulate interaction forces between the brush molecule and its environment. In the images, you can see the backbone for the brush, and you can either see isolated backbones, and you can also see folded sets of molecules or a molecular ensemble. And the brushes can also be seen as a slightly raised area surrounding the backbones. ScanAsyst allows acquisition of images like these for all users, regardless of level, and the results are very consistent with very high resolution. Another polymer example, is looking at alkane chains. These are deposited on HOPG, and they form this crystal structure where the alkanes line up, and the spacing between the length of the molecule is about 7.5 nanometers, and you can actually see within this 400 nanometer ScanAsyst image of the C60H122 alkane, you can see the order of these 7.5 nanometer long molecules on the self-assembled monolayer. And I should note that this molecular resolution was obtained without manual parameter adjustment. The system just adjusted itself. Another application that the Dimension Edge is excellent for is looking at lithium-ion battery research. We actually have a complete solution, including a solvent-compatible EC cell and a glove box for 1 part per million environmental control. Because ScanAsyst works with this system, the imaging in fluid is very easy. There's no need for tuning or anything like that, and this is significant, a significant improvement, step forward for ease of use with these systems. But also, you get new information because now we have unambiguous material contrast, and we can really see adhesion. This is actually, these images are of the SEI layer, which is a very important effect to study within lithium-ion battery research. Another lithium battery, except this is lithium batteries for EV and disposable lithium batteries. This is a membrane called CellGuard. And these images show the consistent high resolution with no sample tearing or tip contamination that's enabled by PeakForce Tapping's direct force control. LEDs are another important industry, and with all our mobile phones using organic LEDs, that's an area that we would like to contribute to also. And one of the important things to look at is the structure of this ITO, or indium tin oxide anode. The properties of the grain structure in the anode can affect electron transport, and also optical properties of the light that's transmitted through it. So having good idea of what the structure of this interface, or this surface is important. ScanAsyst produces high resolution and quantitative structural information needed to analyze the relationship. Oops. Another LED application is in the patterned sapphire substrates. These are for high brightness LEDs, and these substrates are designed with a high dense pattern of micron-sized bumps. The PSS structure is designed to reduce the crystal dislocations and improve optical emission efficiency by reducing internal reflection. For uniform LED performance, or LED performance, bumps must uniformly match the design parameters. For example, we don't want cut-off tops or tilts or anything like that. We need a uniformity of diameter, pitch, height, sidewall angle, roughness, etc. Optical techniques don't have the spatial resolution required to verify that the wafers are meeting design parameters, but ScanAsyst allows automated parameter adjustment for consistent results without user intervention. Another difficult geometry to work with is this deep, narrow trench. These are difficult to image in tapping mode because there's confined air caught within the bottom of these trenches, and that damps down the probe oscillation. So you end up having high force on top of the feature, and low or maybe not even contacting in the bottom of the feature in tapping mode. However, with PeakForce Tapping, we feedback on the peak force, so that's always constant throughout the entire profile, and so that allows you to get into the bottom as long as your tip geometry will allow you to go in there. And you can actually see the difference. There's some variation in the bottom of these trenches in terms of the exact shape of that bottom, so we can actually get a good profile down there. In fluid, ScanAsyst is also very highly functional and automated, and so these are images of DNA imaged in fluid with ScanAsyst, and on the left here we have single strands of DNA. Imaging like this enables studies of DNA-protein interaction, but it's also just a great way to see how well your system is performing, and show that the forces are low. If you engineer your DNA, you can make it form origami or three-dimensional structures like these on the right, and ScanAsyst does great with these as well. And I should remind you that ScanAsyst does eliminate cantilever tuning or set point adjustment, or even feedback optimization for imaging in fluids. So none of that is necessary from the user. Now the Dimension icon, or Dimension Edge, is also a highly stable platform, and this allows long-term studies. So this set of slides is actually, or this slide is about a sample that is a special glass, the lithium aluminosilicate, with a small amount of silver. And when you prepare a fresh fracture surface of this glass, the silver acts as a seed for crystallization. We can identify the seeds because the adhesion is higher for these seeds, and over time, very slowly, you start growing these little crystals off of the silver seeds, and eventually they will cover the entire surface. But this takes 5 or 7 hours. This set of images was actually over about 5 hours. And the drift rate of the system was about 0.1 nanometer per minute, so it was easy to track these features. Now, we've been talking mainly about PeakForce tapping, but I want to remind you that the Edge can do a lot of other modes. The experiment selector that you access when you're first entering the software allows you to quickly and easily open up all kinds of possibilities for SPM experiments. For example, you can produce maps of, you can do tapping mode, so you get a height map. You can get a dopant profile map. So this is a SRAM, and we have the laser turned off during the scanning capacitance measurement, but so we can actually avoid having any photocarriers being excited. But the map there is of the dopant profile without photocarriers. You can also do MFM, and that will give you this is a nickel alloy, and you can see the structure of the magnetic domains within the nickel alloy through MFM. So there's all kinds of different possibilities of other high-resolution measurements that can be done, and this experiment selector makes it quick and easy to open up the possibilities for doing these types of AFM measurements. However, PeakForce tapping makes it even easier. Really, PeakForce tapping is the ideal mode for making AFM easy. It gives you high-resolution imaging, and it's really the easiest thing to do, and it works in both air and fluid. It gives you unambiguous material contrast, making the analysis significantly easier. And now it's available for the Dimension Edge, which is our highest price-performance ratio system available. So with that, I'd like to wrap up and open up the floor for questions. Thank you.